Elements which are showing the electronic configuration 0, 5 and 10, especially I am talking about d orbital, they are considered to be more stable. So all these elements, they shows a color only when it is in a solution state. When you pass the light it, for the observer, it gives a complementary color. If the unpaired electrons are there in the substances or in that element, it will be responsible for giving the color. Hello my dear students, a warm welcome you all. Myself is Purnima, lecturer in Department of Chemistry at Vidhyaashram Pre-University College, Temple of Excellence, Mysuru. My dear students, in our last discussion, we were dealing with the unit called D and F block elements. Under that, we have discussed about the general characteristics of the D block elements. Under that, we have discussed about the atomic radii, ionic radii, and also we have discussed about the density. Is it right? In addition to that, we also discussed about the trends in their property. In that, metallic and ionization enthalpy we have discussed. We'll still continue with the trends in their property by understanding with the oxidation state, magnetic property, formation of colored compound, and catalytic property and formation of interstitial compound and alloy formation in the D block elements. So first I'll go with the oxidation state. All these elements except the last member, they shows variable oxidation state, and all these elements are being metal, they shows only the positive oxidation state. So already we have understood that all the D block elements are metal in nature, and also if you see the oxidation state, they are variable. So why it shows a variable oxidation state and why it shows only the plus oxidation state, or we can say that why it shows only the positive oxidation state, that we are going to understand while dealing with this oxidation state. Okay. The reason for giving different oxidation state are as follows. The energy differences between the 4s as well as with the 3D electrons are very small, and hence 3D electrons are required very little energy to promote it to the 4s. Okay. In such a way that it will easily get promoted to the valence shell. That is why it involves easily with the bonding. That is why they shows variable oxidation state. So first I will take an example by taking nucleus followed by number of shell. So I'll see this is my 3D shell, okay, followed by 4s. So the energy gap between this 4s to the 3D, which is very small, in such a way that the electrons which is present in the 3D can easily jump to the 4s. If it is present in the 4s, we know that this is a valence shell. Is it right? This is a valence shell. If the electrons are available in the valence shell, it can easily donate to the any other element, and easily it can form a bonding, and thereby it forms the positive oxidation state. Why it always forms a positive oxidation state? Because it always loses the electron. It always loses the electron which is there in the 3D shell that can be jumped to the 4s, and it will lose its all the electron, thereby it forms a easy chemical bonding. That is why all this D block element, they shows the positive oxidation state because of the small gap between the 3D to the 4s, where if the electrons are present in the 3D can easily jump to the 4s because of the small gap, and it can easily involve in a bonding by donating its electron. So hope you all understood with this. And oxidation state of this elements, which also depends upon the number of things. One is the number of electrons which is present in the outermost shell. So if I say it is outermost shell, always imagine it is nothing but a 4s shell, and number of unpaired electron which is there in the d orbital, that is in a penultimate shell. So what is meant by penultimate shell? So already I have understood that if it is my nucleus, so this is my third shell followed by what? Fourth shell, this is 1s and this is 2s. Is it right? So if you see this, you can clearly understand that this is fourth shell is nothing but the outermost shell. Is it right? Before to the outermost shell or before to the valence shell, we have what? 3D shell. So how many number of unpaired electrons are there? Okay. How many number of unpaired electrons are there in the 3D orbital, and also how many electrons are there in the 4s, which play a very important role while deciding the oxidation state of this element. And remember, all this D block element, they shows variable oxidation state. How to calculate that? We have a method. Okay, the minimum oxidation state is given only with the 4s electron which are involved in a bonding, where maximum oxidation state will be given to the 4s, where all the unpaired electrons will be there in the, which is involved in a bonding with the 3D orbital. So I'll take a note that calculation by writing that minimum oxidation state, which is nothing but a number of electron which is present in the 4s. So where does the minimum electronic configuration we write? For example, if I say it is scandium, we write the electronic configuration of argon 3D1 4s2. Is it right? So first we will fill for the 4s, then through the 3D. So the minimum electron will be get occupied to the 4s. Is it right? Yes. So the minimum oxidation state, which is nothing but a number of electron which is there in the 4s, and the maximum oxidation state of that substances which is obtained by number of electron which is there in the 3D plus 4s. Okay, 3D plus 4s. Now all these elements which contains 2 electrons in their 4s, hence they have give rise to a common minimum oxidation state, that is +2, except chromium and copper, which shows the minimum oxidation state of +1. So this is the table of the D block element, especially for the 3D series. Okay, you can see that all this element which shows the variable oxidation state. I'll explain you out by taking the scandium first. So what is the electronic configuration of the scandium? So scandium, which is nothing but a argon 3D1 and 4s2. How minimum oxidation state will be obtained? Which is nothing but a number of electron which is present. Is it right? So the minimum oxidation state is +2. Okay, because the 2 electrons will be there, and maximum oxidation state is obtained by adding number of electrons in the 3D plus 4s. Is it right? How many electrons will be there? 1 plus 2. It is nothing but a 3. So it shows +3 oxidation state or with a +2 oxidation state. I'll go with the titanium now. So titanium, which is having the electronic configurations of argon 3D2 4s2. So how do we calculate the minimum oxidation state? Just by counting the number of electrons in the 4s. So there are 2 electrons will be there, and maximum oxidation state will be obtained by number of electrons in a 3D plus 4s. So it is 2 plus 2, it is +4. Is it right? So it will be exhibits A, +2, +3 and +4 is the maximum. Okay. Next, similarly for the vanadium, you can add the number of electrons. So 3 plus 2, it is 5, that is maximum, and minimum is +2. So like that, we used to calculate the oxidation state of this D block element. You can see that +3, +4 and +5 for the vanadium. Similarly for the chromium, it is +2, +3, +4, +5 and +6. You can see that it consists of 5 electrons plus 1 electrons in the 4s. So 5 plus 1, it is 6. But except for the manganese, this is a one element which shows the highest oxidation state. Is it right? Because it consists of 5 electrons in the 3D and 2 electrons from the 4s. 5 plus 2, it is 7, and minimum is +2. Okay. Thereafterwards, you can see that randomly this oxidation state will become decreases. It become what? Decreases. This indicates that when we are writing the electronic configuration from the scandium to the zinc, from scandium to the manganese, the number of unpaired electrons are more. After the manganese, the number of unpaired electrons are become very less and less. So that is why, their oxidation state will be gone decreases after the manganese. But before that, you can see that all this element, this shows the variable oxidation state. So for the 1 mark, they can ask you which element shows the highest oxidation state. So manganese is the element which shows +7 as the highest oxidation state. Okay. Next, the relative stability of variable oxidation state for the given element can also be understood by the basis of extra stability according to the D0, D5 and D10. Suppose if the given element which consists of 0 electron in the 3D shell, or if it is consists of 5 electron in the 3D shell, or if it is consists of 10 electron in the 3D shell, that elements are become very stable. Is that right? The elements will become very stable. You can see here, in case of the titanium, titanium 4+ is more stable than that of the titanium 3+, because you can see that in a 3D one which consists of 1 unpaired electron. And you can see that manganese 2+ which consists of 3D5, and whereas in the manganese 3+, which consists of 4 unpaired electron. But if you write for the 3D for the manganese, it will become 1, 2, 3, 4 and 5. Whereas for the manganese 3+, it will become 1, 2, 3, 4. So this indicates that if the elements which is exhibit in a +2 oxidation state as well as in a +4 oxidation state, always remember the D0, D5 and a D10. These are the stable electronic configurations of the given element. If the elements which is having the 0 electron in the d orbital, if it is consists of 5 electron, if it is consists of 10 electron, all these elements are considered as a stable element. You can similarly take the example of iron 3+, where it consists of 5 electron in the 3D shell, and if it is consists of Fe2+, it consists of 6 electron. Thereby it indicates that if the elements which are showing the electronic configuration 0, 5 and 10, especially I am talking about d orbital, they are considered to be more stable. This is how the stability of the d block element with the given compound that can also be understood. Okay. Next we have magnetic property. So already we have understood that d block element, they shows the unpaired electrons in the 3D shell. Is it right? Yes. So because of the unpaired electron, they also shows the magnetic property, because if the elements which is having 1 or more unpaired electron, it will be responsible for the magnetic field, because it can easily attract it towards a magnetic field. Is it right? So that is why d block elements also, they shows the magnetic property. The paramagnetic nature is due to the presence of unpaired electron, and the magnetic property will be calculated by using this formula, that is magnetic moment mu, which is given by square root of n into n plus 2 Bohr magneton. This is a unit we used to represent for the magnetic moment. Thus, the magnetic moment will be increases with increase in the unpaired electron which is present in that. Hence, the observed magnetic moment will be useful to know the number of unpaired electron which is present in an atom. So, in the first transition series, as the atomic number will be increases from 21 to 25, the number of unpaired electrons will be get increases from 1 to 5 in the 3D shell. Is it right? That is why as we move from scandium to the manganese, the number of unpaired electrons will be increases, so that their magnetic moment is also get increases only when the number of unpaired electron is more. Okay. After that, the number of unpaired electrons will be get paired up. Even though the atomic number will be increases, number of electrons will be get paired up in the d orbital. So that number of unpaired electrons will be started decreasing. So that magnetic behavior or magnetic property will be started decreasing after the manganese. Okay. So, and at the zinc you can see that it is having 3d10, which consists of no unpaired electron because all the electrons which is paired up in the 3d shell. Hence, it is a diamagnetic in nature. If the elements which has no unpaired electron, they are repelled from the magnetic field. Hence, it is diamagnetic. If the unpaired electrons are there in the element, they are attracted towards the magnetic field. Hence, it is termed as a paramagnetic. So, we will take an example so that we will understand how to calculate the magnetic properties of the or magnetic moment of the given element. So, for this calculation, again I am telling you, this question will be asked for 2 marks. Any one of the elements will be given to you from the 3D series. So, you need to calculate the magnetic moment. It is very simple. So, what we used to take? First, we need to find out the number of unpaired electrons. How to calculate this? First, I will go with the cobalt, which is having the electronic configurations of 27, and it is represented as argon 3D and 4s. In 3D, we have 1, 2, 3, 4, 5, 6 and 7. Whereas in the 4s, we have 2 electrons. So, in the 3D, we have 7 electrons. Whereas in the 4s, we have 2 electrons and it is argon. Is it right? Argon 3D 7, 4s 2. So, what is the electronic configuration? It is the argon 3D 7, 4s 2. So, if you arrange it with the d orbital, you can see that there are 3 electrons are become unpaired. So, how to calculate the magnetic moment now? Magnetic moment will be become, so square root of n into n plus 2. So, how many electrons are unpaired here? 3. So, 3 into 3 plus 2. So, 3 plus 2 is 5. 5 3s are 15. So, square root of 15, which is nothing but a 3.87. This indicates that the value of the magnetic moment for the cobalt is 3.87 Bohr magneton. So, it is very simple to calculate. We will see with one more example by taking Fe2 plus as an example. So, in this case, you can see that it consists of 26 electrons and electronic configuration will be argon 3D 6 4s2. Argon 3d6 4s2. If you split this d orbital, which consists of 1, 2, 3, 4, 5 and 6. Is it right? So, I am talking about Fe2 plus state. Is it right? I am talking about Fe2 plus state. What will happen? So, we have removed the 2 electrons from the 4s. So, it consists of how many unpaired electrons? 4 as a unpaired electron. So, the values of n is equal to 4 here. So, 4 into 4 plus 2 is 6. 6 4s are 24. So, the answer is 4.90 Bohr magneton. So, the magnetic moment of the Fe2 plus is 4.90 Bohr magneton. Next, I will calculate the magnetic moment for the Cr3 plus. So, we will see that how to calculate the magnetic moment for the Cr3 plus. Okay. So, first of all, we need to write the electronic configurations of the Cr3 plus. So, first for the Cr, it consists of argon 3d5 4s1, which consists of atomic number 24. Is it right? Now, I have said it is 3d5 4s2. So that if I write for the 3d, this is my 3d and this is my 4s. In 4s, we have 1 electron, whereas in 3d, we have 5 electrons. Is it right? So, this is for Cr. If I talk about Cr3 plus, so we have to remove how many electron? 3 electron now. So, first I will remove 1 electron from the 4s and 2 electron from the 3d. So, remaining electron will be 1, 2 and 3. Okay. So, because I have removed the 3 electrons. Now, how to calculate the magnetic moment now? Magnetic moment will be obtained by mu is equal to n into square root of n into n plus 2. Okay. So, here n is equal to 3 now. So, mu is equal to square root of 3 into 3 plus 2. So, 3 plus 2 is nothing but a 5. So, 3 5 is a 15. Square root of 15, which is nothing but a 3.87 Bohr magnetron. 3.87 Bohr magnetron. This is how we need to calculate the oxidation state of the given element, but be careful while dealing with the Cr3+. Next, we have formation of colored compounds. Most of the compounds of the transition elements are colored in solid as well as in the solution state. The color of this compound is due to the property of absorbed light of certain wavelength from the region of visible part of electromagnetic spectrum. The actual color of the substance depends upon the wavelength or the color to which it gets absorbed from the white light, and color of the transmitted or reflected light of the substance, it is a complementary of the color to be absorbed by the substance. What does it mean? Already by understanding the coordination compound, we have understood that all the coordination compounds are usually shows the different colors. That is mainly because when you take the solution of this D block element, when you added some water, or if you dissolve it in water, or if you take any solution format, and if you pass the white light to that solution, it absorbs the light in the visible region, and when it is get absorbed in the visible region, for the observer, it looks different. For example, it absorbs the orange light, or it absorbs the orange color in the visible region. For the viewer, it will be looks like a blue color. Similarly, if it is absorbed the violet color in the visible region, for the viewer, it will be looks yellow. Similarly, if the solutions absorb the white light in the visible region around red, for the viewer, it will looks green. This is how it gives a complementary color to the observer as it is absorbed the different light in the visible region. So, same thing it will be followed here also. The D block element shows the different colors. The example you can see with the copper sulfate as well as with the potassium dichromate. Copper sulfate is a blue, potassium dichromate is a orange, and you can see that potassium permanganate, which is a pink in color, is it right? So, or violet in color. So, all these elements, they shows a color only when it is in a solution state. When you pass the light in it, for the observer, it gives a complementary color. Next, the formation of colored compound is also because of the following things. The transition metal ions containing unpaired electrons are the vacant d orbitals. Therefore, hence it is colored. Naturally, the transition metal ions have completely filled a d orbital containing no unpaired electron. They become colorless. For example, zinc. It consists of fully paired electrons in the D shell or in the 3D shell. Hence, it will be in the colorless nature. If the unpaired electrons are there in the substances or in that element, it will be responsible for giving the color. Okay. So, the ions which have completely filled a d orbital, that is in a 3d10, which is colorless. Example is zinc 2+, which is 3d10, hence it is a colorless. Similarly, Cu+, which is having the 3d10, hence it is also colorless. The cuprous ions, which is 3d+, which is having 3d10 configuration, hence it is a colorless. But if you take the cupric ion, which is Cu2+, which is having 3d9 configuration, hence it consists of one unpaired electron, hence it will be shows a color of blue. Hence the cupric salts are also blue in color while the cuprous salts are colorless. So what does it indicate? If the unpaired electrons are there in the d orbital, that is in a 3D shell, it will be responsible for giving the color to the substances. If there is no unpaired electron, obviously that substances will be looks colorless. Okay. So you can see that I have represents the color of the all 3D series. The scandium, if it is present in a +3 oxidation state, it is a colorless. If it is titanium which is present in a +4 oxidation state, it is a colorless. If it is present in a +3 oxidation state, it is exhibit in a purple color. Similarly, vanadium, it is exhibit in a +3 oxidation state, it will be green. Similarly, chromium, if it is there in the +3 oxidation state, it is a +3. Manganese, if it is there in the +3 oxidation state, it is a violet. Manganese in the +2 oxidation state is light pink, and Fe2+ in the green. Fe3 plus yellow, CO2 plus pink, Ni2 plus green, Cu2 plus blue, and Cu plus it is a colorless, and zinc 2 plus is a colorless. We can understand by looking at this colors in the transition element. So titanium, if it is there in the +3 oxidation state, it will be color. Similarly, vanadium, if it is there in the +2 oxidation state, it will be colored. Similarly, +3, +4 and +5. Chromium also, if it is there in +2, +3 and +6, which shows the different color. Similarly, you can see that manganese shows a light pink as well as a dark pink in +2 and +7 oxidation state. Similarly, the iron, which also shows light yellow and dark yellow in +2 and +3 oxidation state, and cobalt has +2 oxidation state. If it shows a pink color, and if it is there in a +2 oxidation state with a nickel, which gives a green color. Similarly, the copper, if it is there in the +2 oxidation state, it will give a blue color. So, hope you understood with this how these unpaired electrons play a very important role in giving colors to the coordination compound, especially in a 3D shell. Next, we have catalytic property. So, already while discussing the general property, I have told you that this transition elements which act like a very good catalyst during the preparations, especially with your organic chemistry as well as in the inorganic chemistry. Especially, while learning the P block element, we have understood that for the preparations of H2SO4, we use iron as a very good catalyst. Is it right? So, for the preparations of H2SO4, we use vanadium pentoxide, and for the preparations of the ammonia, we use iron as a catalyst. In almost all the organic reaction, we use nickel, platinum, palladium. These three are the very good catalysts for the reaction, which means to say that it will either increases the rate of the reaction, either it decreases the rate of reaction, but it maintains the equilibrium in the reaction. So, that is why all this D block element shows the catalytic property. Most of the transition elements, metals and their compounds have good catalytic property, and their catalytic property will be considered to be due to the following reason. The first is because of, according to the modern theory of catalysis, the catalyst which forms an intermediate unstable compound with the reactant, and this intermediate compounds are readily decomposed to give a product, and catalyst will be regenerated. It is very important. So, suppose if the reaction is like this, like A plus B giving rise to C plus D. So, A plus B, when it is reacting in presence of any F as a catalyst, it forms what? Intermediate compound. This intermediate product, we know that it is not stable. It must be decomposed to give a product. At the same time, the catalyst which is also get regenerated, and it will be used for the next reaction. This is how, the catalyst which play a very important role in forming an intermediate complexes in the reaction, and on account of their variable oxidation state, the transition metal which forms a unstable intermediate compound readily. Because of the variable oxidation state, it can loses 2 electron, 3 electron, 4 electron, 5, 6, 7, up to 7 we can say. They forms a bonding with a number of elements, and they easily form an unstable complex, which is an intermediate complex. Thereby, it easily forms a product. Hence, it acts like a very good catalyst. And these elements which also provide the large surface area for the reactant to get absorbed by side, and this help in the reaction to occur on the surface of the catalyst. Not only it behave as a very good catalyst, for the reactant, it provide a very good surface. Okay, so that the reactants which come and sit on the side on the surface of the catalyst, so that reactions will be taking place, as we have learnt in case of the surface chemistry. So, the following are the examples for the catalyst as we have used many times. That is iron, which is used in Haber process for the manufacturing of ammonia, and nickel will be used in the hydrogenation of oil and unsaturated hydrocarbon, and vanadium pentoxide is the oxidation of SO2 and SO3 in the manufacturing of sulfuric acid in the contact processes. Next, we have interstitial compound. So, already I have explained that D block elements are nothing but metals. Is it right? So, when they exist in the metallic nature, because they are solid except mercury, if you see that the metals, In the surface of the metal, or in the metal interior, if you see that, some of the vacant sites will be there. Isn't it? Some of the vacant sites will be there. This vacant site or the interstitial site, if it is get trapped by hydrogen, carbon as well as by nitrogen, then such compounds are said to be interstitial compounds. What does it mean? So the interstitial compounds are those which are formed with the small atoms like carbon, hydrogen and nitrogen, which are trapped inside the crystal lattices of the transition metal. Imagine this is a crystal lattice of the scandium or the titanium or any other metal. What will happen? These are some of the vacant site. If it is get occupied by hydrogen or with the carbon or with the nitrogen, it forms what? Interstitial compound. Because on the interstitial side, the small atoms like carbon, hydrogen or nitrogen will get trapped in that. Okay. Such compounds are said to be interstitial compound. Again, the interstitial compounds, the formation of interstitial compound or what are the interstitial compound will be asked many times for the 3 marks or for the 2 marks. You must know this, how it will be formed, and also you must know the characteristics of this interstitial compounds. They are non-stoichiometric and either typically ionic or covalent in nature, and these are the interstitial compound. They have similar chemical property as the parental metal but differs in applicable in their physical properties such as density, melting point and hardness. The interstitial compounds are very harder and denser because of the small atoms like lighter elements which is get occupied on the interstitial sides of the lattices and leading to the close packed structure. Due to the greater electronic interactions, the strength of the metallic bond will be get increases and retain the metallic conductivity. Example, titanium, carbon, manganese, nitrogen and FeH, vanadium, hydrogen, titanium, hydrogen. You can see that the titanium is the crystal lattice of the titanium which is get occupied by the carbon, similarly with the hydrogen. Similarly, the manganese crystal lattice will be get occupied by the nitrogen. Similarly, the iron crystal lattice will be get occupied by the hydrogen. Similarly, with the vanadium which is get occupied by the hydrogen. Which shows that when the interstitial compounds are formed, the interstitial sites which is get occupied by the small atoms like carbon, hydrogen and nitrogen, they forms a very good metallic bond with the other element. And also, they retain their metallic behavior. In addition to this, this interstitial compounds are become very hard and denser because of the strong interaction between the ions. Next is alloy formation. The interstitial metals forms a large number of alloys, and alloys are formed by the metals with those of the atomic radii are similar. The 3D transition elements are quite similar in the atomic side and other characteristics. Hence, the atoms of the one element can constitute the atoms of the other element in the same crystal lattice. That is, on cooling, the molten mixture of the 2 or more transition metal, the solid alloys will be formed. For example, vanadium and chromium and manganese and nickel are used with iron to form varieties of the steel and stainless steel. The alloys like copper and zinc and copper and tin, and which is considered as a considerable importance. So, as we have already studied that alloys are formed by mixing up of any 2 metal. Even though our 3D transition series, they shows similar atomic radii as we move after the manganese, there we can easily mix their elements to form a alloy. You can see that the copper and zinc and copper and tin. So, these two will have an applicable importance in our daily life. In order to make a stainless steel, in order to make a steel, as well as in order to make a alloys, like a brass, bronze and etc. We will mix any 2 elements with a similar atomic radii. This is another important applications of the D block element where it can easily forms a alloy. So, in the next class, we are going to understand how we can easily prepare the potassium dichromate, which is one of the important compounds in the D block element. By this, I like to say that which are all the things which I covered in the trends in their property, try to work out with the catalytic property, alloy formation as well as with their magnetic moment calculation and interstitial compound. Those are the very important questions which has been repeatedly asked in your board. have a look on it. We'll meet you with the next session. Till that, take care, be safe. Thank you.